Okay, so in this video, we're going to be talking about the physics of why we bank curves and why we don't bank curves. And so just to make sure we all are all on the same page, when we're talking about banking curves, we're talking about when the road slants. So typically your roads are perfectly horizontal. But due to reasons we're going to talk about here, sometimes when you're going around a curve, the road will actually come out at an angle. The most drastic example I think about this is when we look at NASCAR tracks. If you're ever watching those, the big curves at the end are banked, and the cars actually go all the way up onto the curve. And so that's a very drastic example, but that is what we are talking about here. It's taking that horizontal road and bringing it up on an angle. It's called banking the curve. So before we get there, let's talk about just a normal car going through a curve. So this is what it kind of looks like. I like this diagram because you can see that you're actually going at a circle. And because we're talking about this portion of the curve is circular, we know that we're going to be dealing with some centripetal forces. So we're going to have that centripetal net force, and we're going to have an acceleration in the centripetal direction. So that means I'm going to move my car up a little bit, and we're going to be dealing with it where our acceleration is directly towards the inside. And so we're going to be talking about our car when it's approximately right here. So it's into the turn, that acceleration is going in the x direction. So if I draw my car here, we're now looking at it head on, so we can draw our forces in the x and y direction. Well, really importantly, we know that our acceleration, we just said, is going to be in that perfectly x direction, which is towards the center of the curve. So this is really our AC. And that's because we have, once again, this circular motion here. If I think about what forces are on the car, I immediately know that there is a force normal, perpendicular to the surface, and a force gravity, down. Well, in this case, there's nothing in the centripetal direction. So if these were the only two forces on my car, I wouldn't be turning. And so you have to think a little bit more critically of, well, what else is going on with the car? If we think back to what we know about what makes wheels roll, we know that there has to be friction. That's what makes a car turn, is having this friction, having those wheels turn, is there is friction in that case. So the only thing that we can manipulate, force normal is not going to be going up. Force normal is always going to be going up. Force gravity is always going to be going down. We can't make any of those point inward, but we know that there has to be friction in here. And so we can actually say that there is some force of friction towards the inside. And you can think about it, that's as your wheels turn, we're changing the direction of that friction. And your direction of that friction is going to be in the centripetal direction. So I'll be answering this down here. What is causing the car to turn when we are not banked? What's causing the car to turn is completely force of friction. Drawing a free body diagram would also be useful for us to draw our sum of force equations. So my sum of forces in the centripetal direction would just be force of friction equals m AC equals m v squared over r. And then we could have in the y direction, and here just be perfectly force normal minus mg equals 0. So therefore, force normal equals mg. So we have that information. But notice when we're taking a curve that's not banked, the only thing that's actually causing us to be able to go around the curve is our force of friction. That's what allows us to make our turn. That's what's going in the centripetal direction. But now let's start to see what that looks like as we bank. So here you can see my example. Well, my circle is still a horizontal circle, and so therefore my acceleration is still going to be in that x direction, or towards the center of my circle. We're going to draw on our forces once again. I know that I still have force of gravity. I have force normal. And we said that we're going to have some force of friction. Well, we know force of friction is actually in towards the, it's around the surface. So really that force of friction would look more like this. That would be the total force of friction. But in our case, we know we're really just worried about the force of friction in the centripetal direction. So I'm going to call that F little fc, force of friction in the centripetal direction. If I were trying to create my sum of forces here, I'm going to be dealing with the centripetal one. Let's just deal with centripetal here. I'm just using a diagram that already existed. So if we look at the force centripetal, we now know that we have this part going here, so we still have that force of friction. But because my force normal is now at an angle, I can break that one up too. Using our math and our geometry, our theta ends up being here. So this component is the component that would be in that centripetal. Notice that both arrows are pointing in the same direction as our acceleration. So I'm going to actually add that in my equation. And why this is interesting is notice when we are on the other side, when you are not banking, the only thing that is helping you turn the make the curve itself is your force of friction. But as soon as you start banking it, your force normal actually adds to that centripetal force. That force normal is helping you turn that curve. That's a really hard phrase for me to say. But that is why we bank. So we come here. Here's your big key takeaway. Banking the curve allows part of the normal force to be in the centripetal direction. So it allows that normal force to aid in the actual turn itself. This is really important because we often find out what's known as the banking angle. The banking angle is the angle needed so that no friction is needed for the car to complete the curve at the specified speed. Now, you might be going, okay, but why? Why do we really need that? It's for safety. What happens if there's ice on the roads? Or if it's just simply wet conditions? In these instances, friction goes to zero. So as that friction goes to zero, you still need to be able to take this curve safely. You still need to be able to get all the way through it. And so in that case, it would be your force normal helping you out. So the banking curve is the angle that is chosen to where you wouldn't actually need friction to get through the curve. So we're going to look at one example that looks like that. So here it says a curve of radius 30 meters is banked at an angle of theta. Find theta such that a car can round the curve at 40 kilometers per hour even if the road is coated in ice. So the first thing I notice is that the road is coated in ice. That simply means there is no friction. So I know when I make my sum of force equations, I don't need to worry about friction. Just like any problem, before I get this started, I'm going to start with a diagram. Or I guess not even before I get started, that is my starting. So I have theta here. I'm going to put my car here. We have FG going down, and we have force normal going up. Now, once again, because there is no friction, these are the only two forces that we need to deal with. As always, in this case that we've seen, my force net is going to be towards that center of that circle. So I need to break down my force normal. Once again, doing my lovely geometry, I guess is what it is, moving our thetas around. My theta would end up here. So this would end up being Fn sine theta, and this ends up being Fn cosine theta. That's really useful because I'm going to create two sum of force equations. So let's just go ahead and start. I'll use the same color to do in the y direction. So in the y direction, I have Fn cosine theta minus Fg. It's negative because they're going opposite directions. Force normal goes up, gravity goes down, so it's a minus, is equal to, well, here it'd be 0 because there isn't any acceleration in the y direction. So we can go ahead and say Fn cosine of theta equals mg. So I went ahead and converted force of gravity into mg. Now in orange, because it's in the same as our centripetal, I can do the sum of forces in my centripetal direction. Well, that's only Fn sine theta. I'm going to set it equal to MAC, and we know MAC is really equal to mv squared over r. And so what I'm trying to find here is theta. I have two different places on where I could find that. I can find it in this equation, but I don't have Fn. Or I could use this equation, which once again, I don't have Fn. So we have a wee bit of a problem here. We have to kind of figure out how to solve these for theta when I don't actually have one of the other variables? Well, we know that if we have two equations that have a consistent variable, so theta and Fn, we can just use any type of system of equations to solve this out. The easiest one to do here is actually dividing the two equations. That is a possibility because these things are equivalent. If I divide this side by Fn cosine theta, I would have to do that on this side, which is also the same thing as dividing by mg. So this is just using our upper level math. So once again, I'm going to say Fn sine theta equals mv squared over r, and I'm going to divide this side by Fn cosine theta, and this side by mg. We can do a little bit of cancellation here. My Fn's cancel, my m's cancel, and this reduces down to sine theta cosine theta equals v squared over rg. And once again, we're trying to find our theta here. While using our trig, we know that sine of theta over cosine theta is really tangent of theta. And now we have something that we can go ahead and evaluate. I will say it is important to notice for this one, as we evaluate it, that it gave us an answer in 40 kilometers per hour, and we don't actually do things in kilometers per hour, and we're dealing with forces. We know that forces, when it's talking about acceleration, it's talking about meters per second squared. So as I evaluate that, the very first thing I need to do is actually come over here and convert 40 kilometers per 1 hour. To get rid of my kilometers, I say 1 kilometers on the bottom. That's 1,000 meters. My kilometers canceled. And now I'm in meters, which is great. I need to get rid of hours, so I'm saying 1 hour, there's 3,600 seconds. And that is a really good conversion rate if you don't already know it, which means that my acceleration is actually, or sorry, not my acceleration, my velocity here. So we can go ahead and put this in. So that's squared divided by 30 times 9.81. And we're going to take the second tangent of that value that we just got. And when you do all of that, so when I said second tangent, I meant inverse tangent there, I was using my calculator. And we get a theta of approximately 22.8 degrees. So what that means is that if you are taking this curve, this one in this problem, at 40 kilometers per hour, you don't actually need friction to get through it if the angle is 22.8. And so we do know that oftentimes there is friction because we're not always talking with the roads coated in ice, which means that you could take the curve faster if you wanted, because friction would be helping you out here. But we can do all of this together and find out this is what this problem is talking about. So now you kind of have an example of how you can solve a question with a banked curve.